You make decisions by asking questions, every single day, often without realizing it. Machines do the same thing, using decision trees, built on a very simple logic. Is this email spam? Should this loan be approved? Click or skip? Fraud or not? In this video, you will understand decision trees, their intuition, the math behind them, and real use cases. Let's look at a simple everyday situation. You want to travel somewhere. To choose a destination, you don't decide everything at once. Instead, you answer a few simple questions, one after another. Each answer removes some options, and keeps only the relevant ones. First question: do you want to travel abroad? In this case, the answer is yes. Next, you set a medium budget. Then, you choose a city experience. By following this path, one final decision remains. Here, the result is Madrid. Early decision systems relied on manually written rules to control system behavior. The logic was simple. If a condition is true, the system applies a predefined action. This approach works for small and stable problems, where situations rarely change. As complexity grows, rules multiply fast, and edge cases become harder to anticipate. Over time, rules are harder to maintain, and small data changes can break the system. With these limitations, machines become indispensable for decision-making at scale. Decision trees are used because they combine simple logic with enough modeling power. They are useful when decisions must be readable, explainable, and directly inspectable. They replace manual rules when rule-based systems stop scaling. They provide a fast, reliable baseline before moving to more complex models. They adapt naturally to data changes and can be trained and updated very quickly. So let's look at the core idea behind how decision trees actually work. At its core, a decision tree makes decisions by asking a sequence of simple questions. Each question splits the data and reduces uncertainty, step by step. The process continues until no further question brings useful information. Structurally, a decision tree is built from three different types of nodes. The root node is the first question, chosen to split the data as effectively as possible. Internal nodes are follow-up questions that keep refining the decision. Leaf nodes are the final points, where the model outputs a prediction. Decision trees are used for two different goals, depending on the type of output you need. First, classification. The output is a label, like spam or not, approved or rejected. In classification, the split criterion is impurity, meaning the groups become less mixed. Second, regression. The output is a number, like a price, revenue, or delivery time. In regression, the split criterion is dispersion, meaning values inside each group get closer. In both cases, the tree ends at a leaf that produces the final prediction. A decision tree grows by asking questions. Each question splits the data into two groups. Before the question, all data sits together in a single node. After the question, the data is divided into two child nodes. Every possible question creates a different split in different child nodes. For example, you could split on price, age, or category, using many thresholds. The problem is that not all questions split the data in a useful way. Some splits mix very different outcomes together, which makes prediction difficult. Other splits group similar outcomes together, which makes prediction easier. So the tree must decide which question produces the better split. When a question is asked, it splits the data into two child nodes. To evaluate that split, the tree follows the same process every time. First, it measures impurity or dispersion in the parent node. Then, it measures impurity or dispersion inside each child node. The child results are combined using a weighted average. This produces a single score that describes the quality of the split. The tree tests many possible splits and keeps the best one. In classification, this means purer child nodes than the parent. In regression, this means less dispersed child nodes than the parent. Next, let's see how we actually measure impurity and dispersion. To choose between questions in classification, a decision tree needs a way to compare them. Impurity is a number that measures how mixed the outcomes are inside a group. A high impurity means different outcomes are mixed together, so the decision is unclear. A low impurity means outcomes are similar, which makes the decision much clearer. Decision trees choose the question that reduces impurity the most. The most common ways to measure impurity are Gini, impurity, and entropy. Now, let's look at the formulas behind impurity. The Gini impurity is a common way to measure impurity in classification trees. It is defined by a simple formula: 1 minus the sum of squared class probabilities. Here, each p sub I represents the proportion of class I inside the node. The sum is taken over all classes present in that node. Each squared probability represents the chance of guessing a sample from that class correctly. The full sum gives the probability of guessing the correct class overall. Subtracting this value from 1 gives the probability of making a wrong guess. That probability is exactly what the Gini impurity measures at a node. Another way to measure impurity in classification trees is entropy. Entropy is defined as the negative sum of p sub I times log base 2 of p sub I. Here, p P sub I represents the proportion of class I inside the node. The sum is taken over all classes present in that node. The log term measures how surprising a class is, with rarer classes being more surprising. Each class contributes its probability multiplied by its level of surprise. When summed together, this gives the average uncertainty of the node. That average uncertainty is exactly what entropy measures. To choose between questions in regression, a decision tree needs a way to compare them. Dispersion is a number that measures how spread out the values are inside a group. A high dispersion means values are far apart, making the prediction uncertain. A low dispersion means values are close together, which makes the prediction more stable. Decision trees choose the question that reduces dispersion the most. The most common way to measure dispersion in regression trees is variance. Now, let's look at the formula behind dispersion. Variance measures how far values are from their average in a regression node. The formula starts by comparing each value to the average of the node. Here, y sub I is the target value of one sample, and y bar is the average value. The difference y sub I minus y bar shows how far one value is from the average. Squaring this difference penalizes large deviations more strongly. These squared differences are summed across all values in the node. Dividing by the number of samples gives the average dispersion of the node. That average dispersion is exactly what variance measures. A decision tree stops growing when asking more questions no longer improves prediction. First case, the node is already clear. All outcomes are the same or very close. Second case, the node is too small, so there is not enough data to split reliably. Third case, no possible split improves impurity or dispersion at this node. Final case, a predefined limit is reached, like maximum depth or minimum samples. When splitting no longer helps, the node becomes a leaf and makes a final prediction. A decision tree learns by repeating the same simple steps at every node. First, the tree tries all possible questions on the data at the node. Then, it picks the split that improves prediction the most. Next, the same process is repeated independently on each child node. This continues until splitting no longer helps and the node becomes a leaf. Each leaf stores the final prediction produced by the tree. There are many decision tree algorithms, but in practice only a few really matter. First, CART. It is the industry standard used for both classification and regression. CART uses binary splits and optimizes impurity or variance to make decisions. Next, ID3 and C4.5. These are mostly historical and educational methods. They use entropy and information gain, but are rarely used in modern systems. Finally, forests and boosting combine many trees to build powerful models at scale. These methods are based on CART-styled trees and improve robustness and accuracy. If you understand CART, you already understand most tree-based models used today. Overfitting happens when a model learns the training data too closely and fails on new data. Decision trees are especially prone to overfitting because they can grow very deep. As the tree grows, it creates many very specific rules that fit the training data perfectly. Eventually, the tree can split the data until almost every case is isolated. To reduce overfitting, we can limit tree depth and require a minimum number of samples. We can also prune the tree or use ensemble methods like random forests and boosting. A good model is not the one that fits the data best, but the one that predicts new data reliably. Pruning means cutting some branches of a decision tree after it has been built. The goal is to simplify the model and reduce overfitting. Without pruning, a tree can learn very specific rules that fit noise in the data. For example, it may rely on exact values like temperature and humidity. With pruning, these detailed rules are replaced by simpler and more general ones. This keeps the tree smaller, easier to interpret, and more reliable on new data. Decision trees are widely used in real-world systems because their decisions are clear and easy to explain. In spam detection, the model asks simple questions like specific words, known senders, or many links. Each answer narrows the choice until the email is classified as spam or not spam. In medical diagnosis, trees follow clinical questions about symptoms, tests, and risk thresholds. This makes decisions interpretable and easier for doctors to justify and trust. In house price prediction, trees split on size, location, and property characteristics. They handle thresholds and nonlinear effects while staying understandable. In all these cases, decision trees turn complex data into clear, rule-based decisions. Decision trees are intuitive and powerful, but they are not always the best choice. First, when data is very noisy, trees can follow random patterns and become unstable. Second, when overfitting is a risk, deep trees may fit training data but fail on new data. Third, trees struggle when relationships change smoothly instead of at clear thresholds. Finally, at large scale, a single decision tree is often not robust enough on its own. That's why decision trees are often combined with other techniques to improve performance. To finish, let's summarize the most important takeaways about decision trees. Decision trees make predictions by asking simple yes or no questions. Each question creates one split, gradually narrowing the decision to a final outcome. For classification, trees reduce impurity, while for regression they reduce dispersion. Single decision trees are easy to understand, but they can overfit and be unstable. In practice, trees work best when combined in ensembles like random forests or boosting. Thanks for watching. If this video helped you, feel free to like, comment, or subscribe.